Hello. You should see the desktop and you should hear me by now. Does that seem okay?
Yeah, I can
Yes.
see
Okay,
the
great.
desktop.
Thanks. Okay, let me get ready. Okay, what we want to do today is, I don't think we have time to do all of it, but we want to explain the ideas of process states and system calls with experiments. Okay, so there's two zip files here that have code in them that we're going to look at. And the code is meant to, whoops, um, it's up there. It's in the for class. I forgot to put it's in the for class folder. It's this one, Windows Systems Call. Okay, so I got the link wrong in the web page, but the folder's up there. Okay, okay. So now one one thing we want to describe is what kind of watch or see evidence that there's really this going on, that this is what Windows is doing, that processes are shifting between the running state, the ready state, and the block state. Okay. Remember, the ready state means well, okay, and then you kind of combine that with our picture from this picture here. Yeah. If you have two processes in memory, the CPU can only be running one of them. So we're going to imagine that we only have one CPU. Okay. And one CPU is only got one program counter, so it can only be executing one program at a time. So one of the programs is the one that's running. The other program is the other program is not running. It's either ready, meaning that it's ready to be put on the CPU at any time, or it's blocked, meaning the other one is really waiting for something to be done for it. Usually it would be blocked waiting, say, for some data from the hard drive. Okay, so a process that asks to read a file, it has to wait till the data from the file gets read into memory. So it has to wait for read file to return. So the program calls read file, and then read file takes a long time before all the data is here. Most of that work to get the data here is done by the hard drive. Okay, the and so the program, this thing waits in the block state because there's nothing for the CPU to do for it while the hard drive is doing its work. Okay, so we want to see evidence that this is really going on. That any individual process is really either ready, running, or blocked. Okay. Oh, and the other thing we want to do, that's this zip file here that has code that shows us that. And then the other zip file wants to show us this idea of, well, in the book, they talk about system calls. Okay. Can we kind of see what's going on with a system call? A system call is when you jump from your code to the operating system code. So, user mode code runs usually the CPU is running user mode code. It's running our programs. But occasionally our programs need something done for them, like start an IO operation. So when a user program wants to start an IO operation, it calls into the kernel using this system call. So your user program calls read file, but read file actually calls into, in the case of Windows, NT read file system call. Okay. And that switches you from user mode to kernel mode. So you're running in kernel mode. Now, sometimes the kernel mode can just do what you need and to return immediately to user mode. Like open file, well, that file operations are like that. Usually, if you call a file operation, you jump from user mode to kernel mode. The file operation, since it requires the hard drive, takes a long time, so you get put in the block state. But there are a few system calls where the user code calls the system code, and the system code just immediately returns an answer right away. But you jump from user mode to kernel mode. Okay, so is there something that can let us see that happening? And it turns out, yes, we can't really directly watch it, but we can get indirect evidence that this is what's happening, that you're going from user mode to kernel mode. So we'll kind of play around with indirect evidence of watching switch from user mode to kernel mode. Okay, and the code that does that is in this other zip file on Windows system calls. Okay, so let's look at the first one. Oops, I want to unzip it. Okay, now these take a little bit of explaining. There's a few simple examples in this folder, and in this subfolder is a bunch of experiments. They're a little bit more elaborate. They're actually pretty interesting. That lets you actually really watch what's going on inside of your computer. Okay, so first let's just start with these simple examples. Okay, here's 3 C programs that are one line, each one's a one-line program. There's 3 one-line C programs. Okay, busy loop 1, busy loop 2, and busy loop 3. And what it is they're actually busy looping in slightly different ways, having to do with this picture. Okay. Okay. So let's keep this picture over here and this code over here, and think about what the C code is doing. Okay. This is here's a C program that puts itself to sleep. What this program does is, this is not unusual in Windows programming. A program doesn't have anything to do, so it wants to wait a little while for something. So the program's deciding it wants to wait. So it calls the Windows operating system with this function call called sleep. And what that is the system call telling the operating system to put this process in the block state for, let's see, put the process in the block state for that many milliseconds. So that's 1,000 milliseconds. Now, in the case of Windows, that's a Windows function call. So if you want to read the documentation for it, you would say Windows sleep function. And here's Microsoft's documentation on it, the sleep function. Okay. See, enter wait state. Okay. So you're being put into the, well, some people call this blocked or waiting. So not everyone uses the same name, but you're asking the operating system to put your process, your process is running, you're running, but then you're saying, put me in the block state for a certain amount of time. Okay. All right. So you have this operating system call, this function. Now this function leads to a system call that says, from the point of view of this picture here, the sleep function would be here, but it would call some system call in here that would say, put me to sleep for 10 seconds, for 1,000 milliseconds. Okay. Now, what does that end up doing? Now, this program, what it does, when after the program's running and it calls sleep, says, put me in the block state for a certain amount of time. The operating system keeps track of how long you're in the block state, and it sets a special timer. And so notice that this is not an IO initiation. It's me. My program tells the operating system, please put me in the block state for a certain amount of time. But then at some point, the operating system sets some hardware timer to keep track of how long that thing has been blocked. When the hardware it's not this, and it's not this timer here. This timer here is the timer for changing who gets their turn. So your motherboard has multiple timers on it. So one timer is used to switch between processes. That's a very special timer. Over here, you would be using some other timer, some timer that would just let the operating system know when the 1,000 milliseconds have gone up. Then this thing becomes ready, okay? And then when it's ready, it gets its turn on the CPU at some point. Okay, now what does this thing do when it comes out, when it's done sleeping? It just puts itself to sleep again. So this thing just repeatedly it's running, but it just keeps putting itself back to sleep. So my program, this is an example of a program that's running almost entirely in the block state. It will be in the ready state for a tiny period of time, move to the running state for a tiny period of time, and in the run state, it just immediately calls sleep and gets put in the block state for 1,000 milliseconds. So This is a program that runs in the and it runs in the block state almost 99.99% of the time. Okay, so that's one thing. Now, here's another busy loop that's almost the same. This busy loop also spends almost entirely all its time in the block state. Here's why. Okay, it's in an infinite loop. Okay, this other one was an infinite loop. Okay, so this is an infinite loop, but every time it loops, it calls printf, and it prints some long string to the console window. It prints kind of a medium long string to the console window. But an IO operation is exactly, calling printf is an IO operation. So that initiates the IO operation, and my process gets blocked while the operating system does the IO operation. So this thing requests a printf. The call to printf goes up here to the system call for printf. Okay, and printf is a form of write file. Printf, the actual system call for printf would be the Windows write file system call, because the console window is thought of as a file. Remember, you could do IO redirection. I can run this program with the IO redirected to a file. So printf thinks it's talking to a file. It actually thinks it's talking to standard out. Printf prints the standard out. Standard out could be the console window, or it could be a file. So from the point of view of Windows, it's really a file. Even when it's a console window, it actually treats the console window as a file. So it's the NT write file system call. So printf would be the NT write file system call. All right. So, but that blocks you. You know, the IO operation takes a lot. Now, but printf doesn't take very long, but from the point of view of the CPU, it takes forever. Remember, the CPU does instructions on the order of a billion a second, a billionth of a second to do one instruction. Writing to the console window, writing this data to the console window probably takes a few milliseconds. That's still, every millisecond is 1,000 CPU instructions, because they're a billionth of a second. So from the CPU's point of view, this simple printf takes forever. So when this guy initiates the file operation to write this data to the console window, it puts this process in the block state because it's going to take a while, and the CPU does something else. Okay, so even a simple little printf puts you in the block state for a few milliseconds. Okay, then when the printf is finished, you go into the ready state. And then at some point, you get this program runs on the CPU again, and it immediately asks for another IO operation. So this program spends all its time in the block state. It spends very little time in ready, very little time in running, just long enough to call printf, and then it spends almost all its time in the block state. But unlike this one, when this one's in the block state, nothing's happening on its part. When this one's in the block state, actually, the CPU and the IO system are working in its behalf. So if you think over here, there's actually stuff happening by the IO system on the behalf of the process that called NT write. So while this process is sitting in the block state, somebody is doing its work for it. Okay, so somebody else is doing the work while it's in the block state. Okay, now, so that makes it different. So these two processes both spend all their time in the block state, but this one is not making use of the CPU in any way. This one's actually making use of the computer, a combination of the CPU and the hard drive and the IO system. Okay, now here's a third one. What this is, notice it's an empty while loop. So what this is it's just CPU instructions that just branch and jump, branch and jump, branch and jump. But it actually is a sequence of CPU instructions that are in just a loop of branch, jump, branch, it's just in a loop. But this thing actually uses up the CPU. So this thing stays in run mode, the running state, for as long as the operating system will let it. So when you run this program, it starts in the ready state, because every program starts in the ready state. Then when it gets its first time to run, it goes into running state, and it chews up CPU cycles doing nothing until it's descheduled because of the timer interrupt. Then it goes back to ready. Then after a little while, the operating system puts it back on the CPU, and it just chews up CPU cycles doing nothing. Okay. and then eventually it uses up its time slice and it gets put back in ready. It'll never be in the block state because it doesn't do anything to block it. It never makes a system call. Okay, so this thing would be running entirely in this state here. Okay. Okay, now you can compile these programs and kind of watch them. There's not a lot to see when you run them. There's really more to think about them, but I'll open a command prompt here. And my C compiler is in the C, oh, I forgot the slash. CS123 CS302 folder. It's in the min.gw folder. It's in the compiler's in the bin folder, and it's the GCC compiler. And I want to compile. I'll compile busy loop 1 first, but the output should be EXE. And then I'll compile busy loop 1. Okay, so I'm going to compile busy loop 1. The compiler output should be named busy loop 1.exe, and that's the compiler. Okay, and then I'll do this for busy loop 2. Compile busy loop 2. The output should be. Notice that C doesn't care a whit about what I named the output file. So if I want to compile busy loop 2 and name the output busy loop 1.exe, C is perfectly happy to do that. It'd be kind of dumb to do it, but you can name the output file anything you want. Unlike Java, where the class file has the exact same name as the source file, C, and you can argue it's maybe not such a bad thing. You can name your source files one way, you can name your executables a different way. Okay, so I'm going to make sure I get this lined up. But you got to make sure you have to make a choice for the there is no automatic, well, there is an automatic naming. If I don't say what the output file should be named, it's called A. That's a tradition in C compilers that's been around forever. The file's called A. Okay, which is usually not what you want your output file to be called. So by default, every executable file is called A. I don't know what A, I don't know. I don't know the history of that, but it's called A. Okay. Okay. So I want compile busy loop 2 and call it busy loop 2.exe. Okay. And I'll compile the third one and call it busy loop 3. Okay. Now, busy loop 1 was the one that just doesn't really use the CPU at all. Okay. Now, if I bring up the, well, actually, let me bring up the task manager. And actually watch the CPU. Here's the CPU. Okay. I wish I had more monitors. This is going to get kind of busy with monitors. Okay. So now let me run busy loop 3. Busy loop 3 was the one that was using up CPU cycles. So if I run it, see, I don't have enough. I have too many CPUs. You don't really see the effect of it because its effect is being spread over 12 cores. Okay. Notice that the CPU utilization is now up to, well, it's creeping up. Yeah. See, the CPU utilization is creeping up. And if I kill this, see, CPU utilization drops a whole lot. Okay. Now, its work was spread over all these cores. What the Windows operating system was doing is every time it put it on the run state, it put it on a different core. Okay. Now, why would it do that? Hey, this is a good question. We're talking about operating systems. Every time the operating system put this process in the run state, it put it on a different core. Does anybody have a clue why it might choose to do that? Think laptops.
So as not to bog down one CPU?
Well, why would it care? It's got 12. Why not? It's got to do the work anyway. So, I mean, what's the difference between it from saying you, CPU 1, do all this work versus, oh, I'll spread all this work over all the CPUs? Why would it spread the work over all the CPUs instead of just saying CPU 1, you do all this? What would be its reasoning?
Is it
Why?
to
Is it to avoid overheating?
Yeah, probably. That's probably exactly why. To avoid, if you make one CPU do all the work, it won't overheat, but it will get hot. Okay. So it would tend to make one CPU get hot, which is not a good idea. So what it's really trying to do is spread the heat around. Okay. And modern operating systems are very conscious of this. Yeah. In the old days, they didn't have to worry about that, but they're actually modern schedulers are very worried about spreading the work around so that no one CPU gets too hot. They won't overheat because the CPUs protect themselves against that. So the CPU is meant not to overheat, but it can get pretty hot. You can make a CPU get pretty warm to the touch if you use it too much. So when I ran that busy loop, the one that just uses up lots of CPU cycles, the work is being spread all over the place, but it does make the total CPU utilization go up a fair amount. Okay. Now, here's a game I can play. See this program? Okay, I've got this program running called Busy Loop. Now, go to the Details tab, find Busy Loop, and right-click on it. And then see there's this thing that says Set Affinity. This is real interesting. Set Affinity allows you to control which CPU the process is running on. So I'm going to set it to run. I'm going to turn off all these other CPUs. And I'm telling the operating system that I only want that process running on, I'm saying now it should run on CPU 0. Okay. So I'm now determining that the operating system should keep that process only on CPU 0. Now go back to performance. Oh, there it is. There, finally. Notice that these things are not in the right order. There it is. See, that CPU is pegged. That CPU is running full steam. All the work now of that one. Now, notice it didn't change the total CPU utilization. The total CPU utilization is about the same, but I've told the operating system to put that one process over here. Now, let me go and change it. Let me go over to Details, Busy Loop, Set Affinity. I'm going to let it have 2 CPUs. Go back to Performance. Takes a little. I think it takes a little while for it to kick in. Now, I gave it 2 CPUs. What's a little bit interesting is it seems that the operating system's decided it's going to keep it on one of them. Oops, no, there it switched a little bit. It went to the other one here's the other one. See, but it seems now notice I don't 5 and 11. I thought I picked 0 and 5. It seems to be doing 11 and 5. Okay. Notice that it's kind of switching it. It's saying mostly on this one, but every once in a while it puts it over on this one. Okay. So it kind of, it's, and then if I want, I can go back over here and I'll set the affinity now strictly to, I don't know. I put CPU 0. Oh, I didn't see that I was also using CPU 11 down here. I forgot about this. So now I'm actually using 3 CPUs. Okay, so turn off that one. Turn off that one. Let's go CPU 1. Okay, now CPU 1 is the one we're picking. There it is. Okay, CPU 1. CPU 1 is taking the full load. See, it switched from 11 to 1 when I told it to. Okay, so now let me see what happens if I give it 2. Set affinity. I'll give it 1 and 5. Go over to performance. Okay, now I switched it from, now it's gotten 1 and 5. Notice that even though I gave it I told the operating system to use 2 cores, the operating system seems to pretty much be some reason sticking with 1 core. It's not trying to balance between the 2 cores. I'm not sure why. Maybe because we set the affinity, so the operating system's thinking, oh, maybe they really do want it on 1 core. So it's mostly using that core. It's not trying to spread the work between the 2 cores very well. Most of the time it's on that core, and every once in a while it puts it on that core. So you can see that now later on in the next chapter, we'll talk more about scheduling, and we're going to talk about these kinds of issues. How does the operating system choose processes? How does it choose CPUs and things like that? Okay. Notice it's starting to seem to be do a little bit more mixing. It seems to be starting as time goes on. It seems to be drifting more towards an even distribution of the work between these two CPUs. Kind of a little bit more evenly distributed. Okay. All right. All right. Now, what about the other ones? Okay, if I kill that, then there's no more work to do. Okay, so see now the computer's back to it's more or less idle state. Most of the the CPU is doing right now the CPU's work the total computer is using quarter of the CPU time. That's probably all Zoom. Probably all that CPU time is going to Zoom, keeping up with the video streaming. Okay, so I bet what work we're seeing here is Zoom working. Its work is being spread over all the cores, but it's probably mostly Zoom that's working right now. Okay, now if I run busy loop 1 was the one that just put itself to sleep all the time. There it is. It's running. Okay, actually, now let me go find busy loop 1, and I'll put it on a CPU, and it won't have any effect on the CPU. So here's busy loop 1. I can put its affinity on CPU 2. I'll put it on CPU 3. Okay, so it's on CPU 3. It'll have no noticeable effect on CPU 3. Okay, because it's sleeping all the time. Okay, it's really actually even though it's running, and it's shown as a running process. The status of the now notice that see the status says running here. That's not this status here. Okay, this is not the status of this thing here, because this just means this is just something else. You can put programs in a suspended state. Okay, there is such a thing as a suspended state. That's not this stuff over here. Blocked is not suspended. Okay, suspended is a special state. It doesn't show up in this picture because it's a Windows thing. I think Linux has something similar. It's like a special kind of block state. Yeah, it's a block state where you're just essentially shunted off to the side and just left. It's kind of an extra block state. It's kind of hard to describe it. It's called suspended. It's actually used for certain purposes. So here the distinction is between running, which running means you're in this cycle. Running means you're in the ready running blocked cycle. You're part of the scheduler. Actually, what suspended means is you're suspended. You're not part of the scheduling process. So this is the scheduling process here. Suspended means you're just not part of it. The process exists, but it's in memory, but it's not part of the scheduling process. Okay, so you will never see one of these things say blocked or ready. It always just says running or suspended. Okay, now busy loop 1 is running. But really what we know is it's almost always in this state here. When it's 1 second comes up, it goes into the ready state. The scheduler puts it in the running state, and it's in the running state just long enough to call sleep again, which puts it in the block state. And calling sleep probably takes a few billionths of a second, because it only takes a few machine instructions to call sleep. So that calls sleep and then gets put in the block state for 1 second. Then after 1 second's up, it goes into the ready state. Depending on how busy the scheduler is, it might stay in the ready state for a few milliseconds. Then the scheduler will get to it in the ready state, put it in the running state, and then immediately it puts itself blocked again. Okay. Now we don't really see. The only thing you might see it's using 0 CPU time, but that's 0% of the 12 cores. So even the one that was busy loop 3, which used 100% of 1 core, was still only 1/12 of the CPU time. So this column's not all that useful. This column is what percentage of the total CPU time 12 cores a process might be using. So even a fairly busy process can show up here as very low. If you use half of 1 core, You're using only 1/24 of the CPU, so that's only what, 4%, 5%. Okay, so yeah, it doesn't show up. Even fairly busy processes don't show up as using much CPU time here. To show anything more than, let's see, what's 1/12? 1/12 is what, like 8%? To show anything more than 8% here, your program would have to be multi-threaded and run on more than one core. To even show up more than 8% here, the program would have to be running on more than one core. If we go back, actually, let's go back and run busy loop 3. Okay, that's the really busy one. Busy loop 3, set its affinity to core 6. I'll put it on core 6. Oh, and wait. Yeah, okay. It's only on core 6. 8%. See? 1/12 of 100. Yeah, about approximately 8%. And there it's using all of one core. So, but that's 1/12 of the computer. Okay. So what looks like something, yeah, it's kind of with a modern computer with so many cores, this kind of stuff can be a little bit misleading. You think, oh, 8%, that's not very much. But if that 8% is concentrated on one core, it's 100% of the core. And if I wait a little while, I'll hear the fans on my computer start up because the CPU will need to start cooling off that core. Yeah. And I do hear the fans kick in after a little while because one core is starting to get warm. So that the laptop notices that and it kicks on the fans because it's got to worry about that one core. It won't overheat, but it does need to start blowing some more air over it. And I do hear the fans start up. Okay. But it's not very often that you would park a process on one core like that. We're doing that as a way to experiment. It would be it's actually done on servers. The reason this process affinity stuff exists is it's used in big systems like on servers. So like a database server might take a part of the database and dedicate one core to it. And maybe dedicate another part of the database system to another core. And it may be actually, and that's what this is there for. On large systems like web servers or database servers, it can actually be efficient to take a certain like subsystem of the database or the web server and put it on one CPU and maybe leave the other CPUs to share the work of other subparts of the subsystem. So Windows gives you the ability to put a process on one or two or whatever subset of cores you want. And Windows provides that feature because it's useful in large systems, database systems, web server systems. Yeah, it's not unusual to dedicate one piece of a large system to, say, one or two cores. Like maybe two cores do one job, another two cores do another job. So different parts of the system their affinity will be set to different CPUs. Okay. All right. Let me see. Then notice I can kill it from here. See, I can kill it from here also, besides killing it over there. Okay. Now, busy loop 2. Now let's run busy loop 2. Now, busy loop 1 doesn't really matter if I leave it running or not. Busy loop 1 is just doing it's using up nearly zero resources of the operating system. So I'll just end it. Okay. Now look at busy loop 2. Okay, it's very busy. See? Okay. Now, but what about its CPU utilization? What about busy loop 2? Okay. Notice that it seems to be real busy, but it's only using 2%, 3%. Now notice that that's only a fourth of what the compute. Oh, we have a name for these kinds of processes. The one that was always in the run state, which was busy loop 3, is called compute bound. Okay, we have a term for it. This thing is compute bound. It'll use up the CPU. It spends almost all of its time in the running state. It's bound to the CPU. It's compute bound. This busy loop 2 is IO bound. It actually spends almost all its time in the block state. This busy loop 1 is just, it's neither IO bound nor compute bound. It's just not using resources. Technically, it's running all the time, but it's actually just in the block state, making no use of system resources. This guy's IO bound. He's in the block state all the time, but the computer is working on his behalf. You can see there's stuff going on over here. The computer is working on his behalf, but it's not CPU bound. It's not really making use of the CPU. It's making use of the other parts of the computer, the console window, maybe the hard drive, and this one's CPU bound. Okay, now when this one chewed up one whole CPU, that was 8% of the CPU of my computer. This guy is only using, we saw, about 2%. See, about 2%. So it's using a lot less resources than the CPU bound one. Okay. Now, see how this graph is doubly shaded? See how it's single, you see there's a light shade and a dark shade? The dark shading is the kernel time. That's the time the CPU is spending in kernel mode. In this picture, that's the time the CPU spends up here versus the time is just that. Then in this picture over here, the light, actually, let me think. They used to color it red. That was a lot better. Now I'm trying to remember which one's which. Actually, I think the dark shade is the, okay. Yeah, no, okay. Boy, they goofed this up. It used to be bright red for kernel times. Now I'm not sure which is the kernel time and which is the user time. The two shades are the time spent in user mode versus the time spent in kernel mode. See, the CPU is either in user mode or kernel mode. It's trying to give us an idea here which mode that the CPU is in. Since see, the thing that's confusing me is the fact that I've got in the background Zoom running. And I think I have a feeling Zoom is running mostly in kernel mode because it's trying to keep up with the streaming. So I have a feeling, but I'm not really sure. Does anybody know? I've lost track now. Windows 10 switched this. It used to be, it was obvious. It was bright red for kernel time and gray for user time. Then some idiot thought that they should use two shades of gray. Anybody know?
The dark blue is kernel.
The dark one is the kernel? Okay. Now, let me kill this. We should see less dark gray because there's no more IO going on. The dark gray would be the kernel time doing IO, but we're getting misleading data here because of Zoom. I think all this kernel time is Zoom. Notice that almost everything right now is running in kernel mode. All my CPUs are busy, and they're almost all busy in kernel mode. And I think that's because just Zoom is taking over the laptop. Huh. I don't have anything else running, but notice that 24% of CPU time is being used. It's being distributed over all these cores, but they're almost all running in kernel mode. Most of the time, they're running in kernel mode. Yeah, normally, if I can't turn off Zoom, but normally on my computer, there's nothing, very little. The vast majority of programs like Chrome and Word and PowerPoint and anything else, the vast majority of programs run in user mode. I have a feeling Zoom is an oddball. I have a feeling that Zoom is running mostly in kernel mode. Now, actually, if I start up Process Explorer, I think I can find out more information. I'm using Task Manager, and Task Manager is really not the best tool for this. So let me start up Process Explorer. Now I had Process Explorer on the website. Remember, it was in, let's see, which folder was Process Explorer in? Oh, it was for the homework assignment. Was it,
It's the homework 2
example?
examples.
Yeah, this one, yeah. I think it's this one has it. Okay, so I can run Process Explorer. Okay, let me collapse some of this tree. I want to find Zoom. Yeah, see, Zoom was launched through Chrome. Okay, so yeah, I launched Zoom through Chrome, so there's Zoom. Now I think I can get a. Let's see if I right click on this. I can get a graph of it showing. Let's see if I double click on it. It's GPU graph. I want to forgot which one.
Performance.
Oh, performance graph there. Okay. And oh, this one's not. See, this one's not doing any CPU utilization. So let me try the other Zoom. Okay. So that wasn't the right Zoom. So let's try. Well, it's not using CPU. No, none of those are. It's not Zoom. Okay. So who's using all that? I'm trying to remember where the we can get a graph. We can get a graph like this in Process Explorer, showing us kernel time versus user mode versus kernel mode. And I'm trying to remember where it is. Okay. Okay, see, here's the old-fashioned red for kernel time, green for user time. Okay, so this computer's using a fair amount of kernel time. Now, but this is the CPU, this is all this is the computer as one. Show one graph per CPU. Okay, now I've got a picture that shows me what each core is doing. Okay, but I still don't know. I want this picture for somewhere in the Process Explorer. I can get this picture for each process to see what each process is doing in terms of its use of kernel time versus user time. So here on my 12 cores, I see a couple cores are doing a lot of work in, it does tell me what, it is Zoom. See, when I hover over that, it is Zoom that's doing that. So process 41452, see, it says zoom.exe 41452. So look for 41452. Was that? Here's the PIDs. Was I looking at the wrong Zoom? Here's another. See, here's another Zoom. But it's not, no, I'm not sure what, this one says, see, there's this one Zoom process that claims it's using lots of CPU of kernel time. But when I go over here, here's 41452 performance graph, and it's not showing any.
If you look at the purple, it's IO. That might be the kernel.
Yeah, maybe. Well, that's what that if it's Zoom, it's going to be doing a lot of yeah, this would be all the IO would be done. So probably that's. Yeah, I'm not. I have to. Probably now. This says CPU utilization. This says IO, but that's usually not. These things are usually not the same thing. But yeah, this is showing a lot of IO See, it's reads and writes. Okay, so that's a lot of IO reads and writes. But I'm still not sure why that's not showing up as kernel time, because it's sure showing up as kernel time over here. It's showing a lot of kernel time over here for that process, but it's not showing it up over here, and I'm not sure why. I'm not sure why this graph and this graph seem to show different things. Does this one and this one doesn't. Notice how this one you could divide up into 12, one for each core. This one doesn't seem to be able to divide up into 12s. It's just showing me 5% of the whole computer. 5% of the whole computer, not 5% of one core. Okay. This is kind of a text version of this. So this performance tab would be the same information in see here it says kernel time, user time. That's the accumulated kernel time and the accumulated user time, but it's not showing much kernel time being accumulated. It isn't showing, even here, it's not showing very much. It's showing a lot more user time than kernel time. So this is not agreeing. It's really not agreeing with what's over here. Okay, so it's actually, this is the oddball, why this one's showing, this one seems to be implying that there's lots of kernel time. Okay, notice that this stuff can be tricky to read. Okay, all right. Now, from our point of view, what we're seeing is 3 different processes, one that runs entirely here, one that runs entirely here. The one that runs entirely here was the busy loop 3. The one that runs entirely here is the busy loop 1. And then the one that's in between is the busy loop 2, the one that's really doing a lot of IO. It's the process itself is blocked almost all the time, but it is making use of CPU resources because I think it's still running. No, let's see. Did I kill it? Oh, I killed it. So it's not running anymore. Okay. If I start it back up again. Let's see. Find busy loop in here. It would be under Explorer, I think. Oops. Oh, there it is. Okay, there's the busy loop process. Okay, see, it's hardly using up the CPU, but see how it's doing a lot of IO. Okay, so now in this picture, we can see how this one is not using the CPU, but it is doing lots of IO. So here, performance process Explorer is giving us a better sense of what's going on. It's only using 2% of CPU time. That's what Task Manager showed us. It uses 2% of CPU time, but it's doing a lot of IO. If we launch busy loop 3, okay, it'll be the opposite. Okay, here's busy loop 2, almost no CPU time, but lots of IO. and busy loop 3, here's busy loop 3. No, see, absolutely 0 IO. But again, see, it shows 8% of CPU utilization. That's really one whole core. Yeah, that's really using up one whole core. 8% is 1/12 of my computer. So this guy's using up one whole core and doing absolutely no IO. And see how this one's a little bit of red? See what lit, oh, that's actually what I wanted to see was, notice that this is entirely green. And what little CPU utilization this one's doing is red. That's because what little CPU utilization it's doing is done in kernel mode. If we can find the right pic, now I've got so many windows up. If you think in this picture, the one that's IO bound is actually spending most of its time setting up a printf. It calls printf, which goes into the NT write system call. It does a little bit of work here, not a lot, but it does a little bit of work here to set up the IO operation. But the setting up of the IO operation is done in kernel mode. And then the IO operation gets done by the IO system. So this guy, the busy loop 2 one, see, he spends a little bit of time in kernel mode and doing a lot of IO operations. But what little time he spends on the CPU is all in kernel mode. Notice that he spends all his time on the CPU in user mode, okay? And he does no IO operation. Then busy loop 1, let's just see what busy loop 1 would look like. Busy loop 1 is the one that puts itself to sleep. Okay, so there's busy loop 1. Let's see what Process Explorer shows us for busy loop 1. Busy loop 1, where'd he go? I don't think these are in alphabetical order. There's 2, there's Did I launch busy? Yeah, I launched busy loop 1. There's busy loop 1. Now I'm trying to find it in busy loop 3. Oh, let's see. Busy loop 2. Does anybody see? Am I missing it? Oh, there it is. Down there. There it is, down there. Okay, there's busy loop 1. Okay. Now, how does busy loop 1 get displayed? Lots of nothing. See? Absolutely 0 CPU utilization, absolutely no IO. See? He's really just, as opposed to this one, a little bit of kernel time, lots of IO work. This one, lots of CPU time. Remember, that's one whole core of CPU time, no IO. And this busy loop here, nothing. It's not even using enough CPU time to show up as even a fraction of a percent. So this one is essentially, because it's in the block state, almost entirely in the block state. So you can kind of see what's going on. These are the three, these are kind of like, okay, this is an unusual process. It's just not doing anything. This is a CPU bound process, and this is what we call an IO bound process. It uses up almost no user time, a little bit of kernel, 0 user time, a little bit of kernel time, lots of IO operations. CPU bound, lots of user time, almost no or none kernel time, and no IO operations. Okay. This middle one is memory usage. We're not private bytes. This has got to do with memory usage. Okay, so we're not really concerned. We're not talking about memory usage. Notice that this guy doesn't see. This guy uses. They all use about the same amount of memory. They're just a small C program. So in terms of memory usage, they all about agree because they're just a small C program. Okay, all right. So one lesson here is how you can use Windows to watch things. I mean, Process Explorer and Process and Task Manager let us do things where we can just watch. And the idea is that we can just watch things that are happening. Now let's do another experiment. I'm going to close this. I'm gonna switch to a different program and do a different experiment. Close all these guys. Okay. Okay. Instead of doing these, okay. Oh, let me show you real quick something. There is not a lot of documentation out there in the world about the deep technicalities of the Windows operating system. There's a ton of books about the internals of Linux because the source code is public. So anybody and his brother who wants to can write a book about Linux. In fact, there's really only like 2 books about Windows internals. Okay, and they're produced by they're both produced by Microsoft Press. This is one of them. It's called Windows Internals. And if you go to Microsoft's website, they make a sample chapter of the book available for free. And the sample chapter of the book they make available for free is a chapter about processes. Okay, so well, I'm sorry, that's the website that makes it available. Here, this is what I want. Here's what the cover of the book looks like. This is the 5th edition. This was on Windows Vista, and the 6th edition was on Windows. Let's see. This was Windows Vista. This probably was Windows 8, and I think there's now a version on Windows 10, or they're in the process of writing it. Though from the point of view of this book, not a whole lot changes. This is the most technical book there is describing the internals of Windows. Okay, and it's a 2-volume set of books. Each volume is 1,000 pages long. Okay, he's the guy who's in charge of the kernel at Microsoft, and there's 2 volumes. They make the chapter 5 and chapter 6 available for free. So right now we're reading chapter 5 and chapter 6, processes and security. Okay, so it's kind of, from our point of view, there's the stuff on processes. That's what we're talking about. So you get past the table of contents, and then you get past the introduction, and then here's the beginning of the chapter 5 on processes, threads, and jobs. Okay, and this is our textbook is talking about things in general. This is the specifics of everything our textbook is saying, but the specifics and the details for Windows. It's fascinating stuff. If you ever want to become a Windows expert, the kind of person who really says, like, there's not a lot of people like that around, but people who work, say, write device drivers. If you were ever to get a job where your job was to write device drivers for the Windows operating system, you'd have to start reading this book. Okay, so this is the book that's mostly what this book is for. It's for the people who have to write device drivers, or people who write real low level or super high performance Windows programs, who really, really, really need to exploit the operating system entirely. Okay, so it's kind of interesting. The diagram we've been looking at for states is in here. I don't know if I'll get, oh, there it is. Okay, there's this diagram in general turns into that diagram for Windows. Okay, that's the state diagram for processes. Okay, notice the suspended is not even in there. Remember we mentioned a little while that some processes can be suspended. This one, they didn't even put suspended in there because suspended is considered out. This is the scheduler states. Suspended is you're outside of the scheduler and your process is just not even part of this system. So suspended doesn't even show up in here. Okay, but if you read this book, like, see here, you can see it'll talk about what suspended means. If you want to know what suspended means, it'll be in here. You can create processes suspended. Okay, so they would tell you in here what it means to be in the suspended state. That's one of the uses of a book like this. The details can be gotten from this book. Oh, Process Explorer was written by the guy who wrote this book. Process Explorer is written by him. So he's the person who wrote Process Explorer. He wrote this book, and he's also the guy at Microsoft who's in charge of the kernel. Okay, so actually, there's some of the details of how Process Explorer works is in this book. This book makes use of lots of screenshots of things like Process Explorer. To get to one. See, that's Process Monitor. It's another one of his programs. That's a screenshot of Process Monitor and Process Explorer. So he uses screenshot. He uses Process Explorer to describe what he uses it to describe what we're doing. He uses it to explain how things work. Oh, notice he has a lot of experiments in his book where he's trying to do what we're doing. Experiments where you run some program, run Process Explorer, and try to watch what's happening. And he's got lots of those in this book. He just shows you lots of. Now, most of these experiments require to use what's called a kernel debugger. So they're not something we can do online over Zoom. So most of these experiments require to use a much more sophisticated software than just Process Explorer. But every few pages in this book, he has an experiment where he wants you to run something, watch output. And he usually shows some screenshot of a sample of what the output could be. Okay, so he's doing pretty much what we're doing here, trying to watch what's happening, trying to show you what's happening, run simple little programs and try to watch indirectly through things like Process Explorer, Task Manager, Process Monitor, try to watch what's happening. Okay, now let's switch to another set of examples. Okay. These examples are trying to distinguish what's going on between the processes that are in the CPU bound processes, the processes that just sit there running on the CPU, versus the IO bound processes like Busy Work 3, the ones that are blocked all the time, but they're really asking the operating system to do work for them all the time. So this is kind of like the distinction between CPU bound, compute programs, and block IO bound. So there's a group of examples here that are the compute programs that are CPU bound. And there's a group of examples here that are the IO bound. Okay, and we want to see what happens when you start mixing them. How do they behave and what happens when you mix them up? Okay, so I wrote this program here called compute program. It's kind of, here's what it does. Now, most of these, you should run them from a command line. Okay. This program here called compute program uses up this, it's like the busy loop 3. It just uses up the CPU. Okay, but it does it in an interesting way. So if you run it, it's a more sophisticated version of that program, busy loop 3. When you run it, it tells you that you need a command line argument. It wants to be told how many seconds it should run for. So I'm going to run it for 5 seconds. Now, what this thing does, it runs for 5 seconds. It times itself. As it's running, it's keeping track of how long it's been running for. When it gets 5 seconds worth of CPU time, it stops. Now, one of the things we're going to distinguish is not wall clock time. This is actually 5 seconds of CPU times, 5 seconds in the running state. So it's not counting any time it's spent in the ready state when it was not its turn on the CPU. So this column is showing how the program is keeping track of how much CPU time it's actually got. This column is telling you which processor it's actually running on. So notice that the operating system bounced it around. The operating system bounced it around. I have these 12 cores, and that process bounced around from core to core. Now, it also shows you which cores it was allowed to run on. So the program is showing you what its affinity mask was. Okay, it's showing you that that affinity mask. There's not 4,000 CPUs on my machine. This affinity mask is a bit mask. What that means is that there are 12 bits worth of CPU. If you go over here to the task manager, and you look at Affinity, what you have to do is think of these as each of this is a bit. Bit 0 up to bit 11. Each time you check one of these boxes, you're setting that bit. And then this mask is showing you the value of that in decimal, but it's reading it as an integer, a binary integer. So for example, CPU 0 would show up here as mask 1. If you turned on CPU 0 and 1, it'd show up here as mask 3, because 1, 1 in binary is the decimal number 3. Okay, now let me show you, we can see that. Okay. I'm going to run this guy for 1,000 seconds. Okay, so he's going to run for a long time. Now I'll go over here and look him up in the task manager. So he's compute bound. Okay, and I'll go over here and I'll set his infinity. And you'll be able to watch over here how the affinity is going to, mass is going to change. So, well, kind of. See, this is a modal. Let's see. Can I get both of them to show up? Let's see. Shunt this over to the side. Make this guy a little bit smaller. Okay, now you can see both. Now bring up the modal box. Set affinity. Okay, I'm going to set the affinity. Oh, it didn't change over here. He didn't update his affinity. Notice that I have to check that. Notice that he's only running on processes 0. Notice you see over here, see processors 0 and 1. Okay, so he's only running on processes 0 and 1, but the affinity mask didn't change. I have to go look why. I could be that I'm not updating the affinity mask variable. Okay, now if I go over here, set affinity, I'll set it to 5 and 6, turn off 0 and 1. I have to click OK, I think, for it to take effect. So I click OK. Oh, see, now he switched over to 5 and 6. But the affinity mask is not changing. I got to go fix that. I wanted the affinity mask to update. Then here it shows us what it's his process ID. See, he's process 46396. See, 46396. So each line shows you the ID of the process, what its current affinity mask is, but that doesn't seem to be working right now, which core it's actually currently running on, and how much CPU time it's accumulated so far. Not wall clock time, CPU time. Okay, I have to fix that affinity mask variable. All right. Oh, and the affinity mask variable is supposed to be the bits you set over here. You think of that as a binary word. So when I set, for example, if I did this, I should have seen the affinity mask be 5. Whoop. Oh, was I doing the wrong process? I was probably doing the wrong process. I thought. Oh, he died. He finished his 1,000 seconds. Okay. Okay. All right. So now let's do another experiment. Too many windows. It's hard to keep track of all of them. Okay. What I want to do now is run 2 compute-bound programs on the same CPU, so that they're forced to share the CPU. Okay. Now, the way I do that is I wrote a batch program here called do computes, or actually it's do compute. What do compute does, if I open it, no, I'm sorry, it's do compute. I have to remember which one's which. No. Oh, I'm sorry. I'm trying to remember how I wrote these things. I'm drawing a blank now. See, that launched 2 of them. See, that's supposed to, if I remember right, see, that should launch one that runs for 10 seconds and one that runs for 5 seconds. See, there's, which, that one ran for 5 seconds, and this one runs for 10 seconds. So it launches 2 of them, okay? So, yeah, if you, this program runs for a specific amount of time, and then this little batch file lets you run multiple of them, okay? It lets you run several of them, okay? Now, what I want to do is what happens if I run 2 10-second jobs on one CPU, okay? Now, if I run it like this, they're going to be put on their own CPU because I let the operating system move them around. You can see they're actually moving all around and they'll run for 10 seconds. Okay, so they each run for 10 seconds. What I'm going to do is here's what I want, one last experiment. I'm going to go to Task Manager and I open the CMD that I'm running here. Okay, trouble is I have too many CMDs. Let me get rid of one of them. Keep this one. Okay, here's my CMD. I'm going to set the affinity of it to just 1 core. Okay, that CMD can only use that one CPU. Now, when I launch children from this CMD, they inherit the affinity of the parent. So now if I launch 2 of these processes, they're all children of this CMD, so they're all going to run on 1 core. So now I have 2 of these guys that they're forced to share 1 core. Notice that they run slower now, because now they're alternating sharing the core. And if you time it, you'll see that it's going to take 20 seconds for the 2 of them to run, because now the 2 of them each are doing 10 seconds worth of compute on, oh, notice that one of them, they weren't quite in sync with each other. And one of them for some reason, the operating system gave one of them a little bit higher priority. So he got his work done first, and then the other one got to do, but notice that they basically were sharing 2 CPUs. I'm sorry, they're sharing 1 CPU. Okay. Now this probably now see processor one. See, oh, now the affinity mask is correct. See, the affinity mask is correct, at least when it starts up. Okay. So now the operating system didn't quite balance them 50-50. So one of them got done a little bit faster. From our point of view there, we had 2 processes that were CPU bound, but they're sharing one single, so we're really in this picture here, 1 CPU, 2 processes. Since the CPU can only run one at a time and each one wants to run for 10 seconds, it took a total of 20 seconds to run both of them. Now, I can do one more experiment. I have a program in here called time this. Okay, so if I time this thing here, time this times how long it takes for this guy to work. Okay, I'm running 2 programs for 10 seconds each. And time this should show me that the result is taking 20 seconds because they're really running on only 1 CPU. Oh, it failed. Time this didn't time I didn't run it the right way. Time this basically launched the other programs and then died. So it didn't time the time it took for those programs to run. It only timed the amount of time it took to launch them. So you have to do this in the right order. So I didn't do that. By doing it this way, I was only timing how long it took to launch them, not how long it took to run them. I have to do that experiment a little bit differently. You could just do it with a timer. You could just use a timer and you can just time. You'll see that that takes 20 seconds to run. Okay, takes 20 seconds to run because 2 computers using 10 seconds of CPU time on one CPU takes a total of 20 seconds to finish. Okay, so we'll do a little bit more experiments with this on next week. What we want to do is mix those CPU bound processes with the IO bound processes. Okay, and what you see is that when you mix a CPU bound process with an IO bound process, neither of them takes longer. If you mix 2 CPU bound processes, they take longer because they share the CPU. If you mix a CPU bound process with an IO bound process, they don't interfere with each other because one of them is using the CPU and one of them is using the IO system so that they can run in parallel. So you see that the CPU bound and the IO bound don't interfere with each other, which is one of the hearts of modern CPU of computing. This idea that you want to interleave CPU bound with IO bound because that's efficient. CPU bound and IO bound don't interfere with. This is referred to as asynchronous programming. They're running asynchronously or parallel programming. The thing that's using the CPU isn't affected by the thing that's using the hard drive. Two CPU bound processes collide, so then you need more than one CPU to handle them, or they take longer. But a CPU bound and an IO bound process don't really interfere with each other because one's over here and one's down here. So we'll be able to do that with these by combining IO experiment. Like let's just show you. If you run one of these, that's a little script that downloads a movie from the internet, a 1 gigabyte image from the internet. I'm downloading a 1 gigabyte image from the internet off of a server. So that's a heavy duty IO process, and it takes about a minute for it to run. Okay, and so this is something that takes a long amount. So you can interleave this IO process with a CPU bound process, and you see that they don't really affect each other at all. Okay, so that was downloading 1 gigabyte. See, that downloaded a 1 gigabyte file off of the internet. It's an installer for something. Yeah, it's a 1 gigabyte installer. So I just point a little batch file at it. I point a little batch file at this installer on the internet, and I get a lot of IO operations. So I'm using this wget program, wget pointed at the URL of where that file is on the internet, and I get instant IO operations, a lot of them. Okay, and so we can interleave now IO operations with CPU operations and do interesting experiments. Okay, so we run out of time, so let me quit here. Okay, if you have questions about this stuff, there'll be another programming assignment up, but hopefully by the end of the weekend, there'll be another programming assignment. But if you have questions about the current one, if you're still working on the programming assignments, let me know, send me email or come to office hours. Okay, and I'll go ahead and try these experiments at home. If try playing around, especially if you like operating systems. We're seeing now ways to experiment with fairly sophisticated tools. We're doing, we're starting to use the tools in pretty interesting ways. Try doing this stuff. See if you can come up with your own experiments even. Try to mix IO with CPU and see what happens. Okay, so I'm going to stop sharing and have a nice weekend. See you next week. See you Monday.